Okay, I'm recording. Okay. Okay, so the recording started. Okay, so there's no questions about the homework. I'm talking about theorem 1.4.4. If B and C are both inverses of A, then B equals C. So I'm proving this now. So B and C are given to be both inverses of A. And so that implies, well, B is an inverse of A. And so that implies that BA equals I. Now multiply both sides on the right by C. And so that gives you that BAC is equal to IC, which equals C. Okay, so BAC is equal to C. But then also, if you have, but it is also true that BAC is equal to BAC. And since C is inverse of A, that means that AC is equal to I. Okay, so AC is equal to I because A is an inverse, C is an inverse of A. And so that's equal to B. So BA times C is equal to B. And we already have that BA. We already have that BAC is equal to C, but now we have BAC is equal to another set, the other event B. And so that, okay, so we now know that both sets B, that both events, both sets B and both matrices B and C are equal to BAC, right? C is equal to BAC and B is equal to BAC. That implies that B is equal to C, okay? So we have that B equals C because both B and C both equal the same set BAC. And you're done. And so that's the proof of this theorem. And so what's this, our conclusion? Our conclusion is that a matrix has exactly one inverse. And that's because if you have two inverses of the same matrix, they have to be equal. So it says here that if B and C are both inverses of A, then B equals C. And so that means that the inverse of a matrix is unique. A matrix has exactly one inverse. That's our conclusion from that theorem. This is the conclusion from theorem 1.4.4, this theorem. Okay. If A is invertible, then its inverse will be denoted by this symbol, right, with A superscript -1. Okay, and so thus we have that A inverse is equal to I, and A inverse A is also equal to I. And so I'm going to denote this by 1. I'm not multiplying by 1, I'm just denoting it by 1. And so A inverse equals the identity matrix, and A inverse A also equals the identity matrix. Theorem 1.4.5 says the matrix A, which is equal to this 2 by 2 matrix, okay, so given that this 2 by 2 matrix, so the matrix is invertible if and only if AD minus BC does not equal 0. In which case, the inverse of that matrix, because it's invertible, is equal to 1 over AD minus BC times the matrix, where you switch these entries on the main diagonal A and D, you switch them, so this becomes DA, and then you negate the other ones off the main diagonal. So this becomes negative B and negative C. That's how I remember it. Okay, so theorem 1.45 is very important. It says, given a 2x2 matrix of this form, A, where you're calling the entries little a, B, C, and D, that matrix is invertible if and only if AD minus BC, meaning this entry times this one minus this times this, AD minus BC is non-zero. In which case, since it's invertible, if this happens, its inverse is given by 1 over A times D minus B times C times the matrix, where you switch the main diagonal entries and you negate the entries off the main diagonal. All right, and so this gives you the ability to find the inverse of a matrix and determine whether or not a 2x2 matrix is invertible. So this works for 2x2 matrices. Okay, there's another important thing called the determinant. The determinant of a 2x2 matrix A is equal to AD minus BC, or another notation for it is this symbol. So maybe if I can vertical. Or you can write it as a vertical line like this, where AD minus BC. Okay. So when you have your matrix A, you could say the determinant of A is equal to AD minus BC, or instead of the bracket around that matrix, you could put a vertical line. So that means you're taking the determinant of that matrix. So this is the matrix, and if you, instead of the brackets, you have vertical lines, that means it's the determinant of that matrix, which is still AD minus BC. Okay, and so DET of A, which is equal to, again, this notation here that I drew, is equal to, is the determinant of a 2x2 matrix A, where A is equal to this matrix right here. Right, so with this theorem, we have a means of determining whether or not a 2x2 matrix is invertible and finding its inverse if it is invertible, and finding its determinant. Okay, so we have many things in this section right here. Okay, and in fact, this is so important that I'm going to there we go. I'm going to put it inside of this section right here. Okay, so this is very important. It's not separate from the lesson, it's part of it, but it's very important. So in between that is this theorem and some details. Right, and so I mentioned a good way to remember how to compute the determinant of a 2x2 matrix, and so I'm just going to write that down here. You have the determinant of a matrix A, which you can write as the vertical line A, B, C, D, right, where these are the entries. It's equal to, now a good way to remember this, because it's kind of easy to just look at the formula and think, how in the world am I going to remember that? It's AD minus BC. Okay, so if you remember these lines I'm drawing, you're just multiplying in those directions. And then it's going to the right, so it's positive, and then this one's going to the left, and it's negative. So it's A times D, the arrow's pointing down right, then the minus B times C, the arrow's pointing down left, minus, plus this product, minus that product. AD minus BC. So that's a good visual way to remember the determinant of how to calculate the determinant of the matrix. So let's stick with the whiteboard. And so let's do example 7. Example 7. Determine whether A is invertible, and if so, find its inverse. So the matrix A is equal to the matrix 6, 1, 5, 2. Okay, so that's our matrix. 6, 1, 5, 2 are the entries. And so to do that, let's find the determinant of the matrix. So the determinant of A, is equal to, you just cross multiply it. So it's 6 times 2 minus 1 times 5. That's equal to 12 minus 5, which is 7. And that does not equal 0. Right? So remember, you just cross multiply. So 6 times 2 minus 1 times 5 is the determinant. 6 times 2 minus 1 times 5. 12 minus 5, which is 7. And this does not equal 0. So the determinant does not equal 0. And so since the determinant does not equal 0, we have our theorem over here that says AD minus B, which is the determinant, right? AD minus BC is the determinant. And so what we found was it was non-zero. If and only if means two statements are equivalent or they have the same truth value. And so since it's true that AD minus BC does not equal 0, it's true that A is invertible. And so by theorem 1.4.5, we deduce, since we know AD minus BC now is non-zero, that A is also invertible. And so this implies that A is invertible. Makes sense? By the theorem. By theorem 1.4.5. Okay, so now our matrix is invertible. It also, the theorem also says, theorem 1.4.5 says, in which case, if it is invertible, then its inverse, A inverse, is equal to 1 over AD minus BC times this matrix. So you're now given A inverse here from that theorem, because you've already found that it's invertible. And so that also implies, continuing from here, that implies that A inverse is equal to 1 over the determinant, which we found AD minus BC, that's the determinant of A, times the matrix D here and A here, negative B here, and negative C here. So you're just switching these two entries. Instead of AD, it's DA, and negating these off the main diagonal. So this is equal to 1 over determinant of A is 7. So it's 1, 7 times the 2 by 2 matrix, where the D is the 2. The 6 is the A. So one good way to remember it is just like this arrow diagram. You don't have to think of it in terms of symbols, right? And memorize the formula. You can think visually about, you can look at it visually. So you're switching the entries on the main diagonal. You're switching the 6 and the 2. So now it's 2, 6. And then these two you're negating. So this is negative 1, negative 5. It doesn't mean it's negative. It means it's the negative of this. So if this entry was negative 1, then that entry would be 1. Okay, so you're negating those entries, and you're getting -1, -5. So A inverse is now 1/7 times that. And so you multiply a matrix by constant by multiplying every entry by that constant. So this is 2/7, -1/7, -5/7, and 6/7. And that is A inverse. And so we not only showed that A is invertible, we also found its inverse, and we're done. Make sense? Any questions? Okay, so that's example 7. Let's look at example 8. Example 8. Solution of a linear system by matrix inversion. Okay, so we want to solve a linear system by what's called matrix inversion. So first, here's the problem. It says solve the linear system. And so you're given the linear system U equals AX plus BY, and V is equal to CX plus DY. Okay, so the proof, let's replace the two equations by a single matrix equation. So we're going to replace this with a matrix equation. And so that matrix equation is just, if you think of the solution U and V as one matrix, the solution matrix, this is equal to the coefficient matrix A, B, C, D times the unknown matrix X, Y here. Okay. So this looks weird, but we've actually replaced two equations with one equation. We replaced two algebraic equations with one matrix equation. How? Well, in order for two matrices to be equal, they have to be the same size, and the corresponding entries, have to be the same. This is a 2x1 matrix, 2 rows and 1 column. This matrix is 2x2. And it's being multiplied by a 2x1 matrix. And so when you multiply the matrix A, B, C, D by X, Y, you're getting a product of two matrices that you can multiply because the inner entries here are the same, and the outer entries determine the size of the matrix. So this resulting matrix is a 2x1 matrix. And so both sides are 2x1 matrices. Now, if you multiply these two sides out, what you get is that, now I'm not, in a sense, I'm not doing this. I'm just putting this as a note. This is the equation we wanted. On the side, the product of these two, what it equals is, if you take the first row times the first column here, it's AX plus BY. Right? This is a 2x1. The product of those two matrices is a 2x1 matrix, right? If you multiply this matrix by this matrix, what you get is a 2x1 matrix where the first entry in the first row, first column, is AX plus BY, and then the second entry, the entry in the second row, first column, is CX plus DY. Okay, so saying that this matrix equals this, saying that this matrix equals the product of these two matrices is really saying that this matrix is equal to this matrix. But if this matrix is equal to this one, then what that also says is that U equals AX plus BY, and V is equal to CX plus DY. Because the only way two matrices are equal is if they're the same size, which they are, and corresponding entries are equal, meaning U equals AX plus BY, and b is equal to cx plus dy. So you can see that now we have u equals ax plus by, and we have that v is equal to cx plus dy. So we replaced two algebraic equations by one matrix equation. But really, for the matrix equation to be true, you need the two equations to be true. So that's why you can do that. And you're saying the same thing. Okay, so we've now represented our linear system in terms of a matrix equation. Okay, so if we assume that our coefficient matrix is invertible, what I'm going to do is I'm going to put a little space here. If we assume that our coefficient matrix is invertible, or that AD minus BC is not zero, does not equal zero, then we can multiply both sides by the inverse of the coefficient matrix and solve for the matrix. Solve for this matrix. Okay, and the coefficient matrix is just this one, A, B, C, D. Okay, so if we assume that our coefficient matrix A, B, C, D here is invertible, or the AD minus BC is not zero, then we can multiply both sides of the equation by the inverse of the coefficient matrix and solve for this matrix. So what I mean by that is, I'm going to have to go to the next page. So what we have is that UV, I'm just rewriting right now what we already have. We have UV is equal to the coefficient matrix of that linear system, a 2 by 2 matrix A, B, C, D, times the matrix for the variables, which is x, y. And now given that, if we multiply in the left of both sides of that equation by the inverse of the coefficient matrix, because we're assuming it's invertible, meaning its inverse exists. So I'm going to multiply both sides by the inverse of that matrix. So I've just taken both sides of the original equation, multiplied on the left by this, the inverse, right? You have this, you multiply on the left here by this, and you multiply on the left here by that. Now, this is the product of a matrix and its inverse, and that means it's the identity. And when you multiply something by the identity, you just get the matrix itself. And so this is the same as xy, because now it's just the identity times it, which is that. And now what we've done is we found that xy is equal to the product of the matrix A, B, C, D inverse times UV. All right, and so that implies that the matrix xy is equal to, well, the inverse of that matrix is 1 over AD minus BC times, you switch the main diagonal entries, so you have dA, you negate the off diagonal entries, so you get negative B, negative C. And so now this part is this part, and you still multiply it by UV. And now you have solved for xy. And so that implies that, well, so the original problem was said, solve the linear system. Solving the linear system means solving for the unknowns, in this case, x and y. So that means x is equal to, so x is equal to 1 over AD minus BC times, because you have this thing here, and so you get UD minus BB. or du minus BB. You're just saying du minus BV. This, when you multiply these two matrices, the first entry at the top here in the first row, first column is du minus BV, and then you're multiplying by 1 over AD minus BC. So that's x. And y is equal to still the constant 1 over AD minus BC. Times, right, because y is this second row first entry, second row first entry. So that means the second row first entry is going to be negative CU plus AV here, or negative CU plus AV is AV minus CU. And it's still times that, right? So you have that. So x and y are that, and we've now solved the linear system, and we've solved it using multiplying by the inverse matrix of the coefficient matrix. Okay, or called matrix inversion. Okay, but this is all given an assumption. If we assume our coefficient matrix is invertible. Okay, this is if we assume that our coefficient matrix is invertible. So with that assumption, we can solve the linear system. Okay, so given a linear system, right, you can represent it as a matrix equation. And when you take a linear system and represent it as a matrix equation, you're going to have a coefficient matrix like this. If that coefficient matrix is invertible, then you can solve the linear system in this way. If it's not invertible, then you have to solve it another way. Okay. So I'm not saying this works in every situation. I'm saying if the coefficient matrix is invertible, then you can solve the linear system. It has one solution, and you solve and you find that solution, the x, or you find the values for each unknown this way. Okay, any questions? It's the end of the proof, so I'm just putting a box here. It's a box. So this is theorem 1.4.6. If A and B are invertible matrices with the same size, then AB is invertible. And the inverse of AB is equal to B inverse A inverse. Okay, so proof. Well, if you start with the matrix AB, and let's say you multiply it on the left by B inverse A inverse. Okay, so let's take the matrix AB and multiply on the left by B inverse A inverse. Well, then what happens is that the A inverse times A becomes the identity. So you get B inverse IB, and because the I is A inverse times A here. And then you get B inverse IB, which is B inverse B, but B inverse B is I. And so what we just showed is that this tells us that B inverse A inverse AB is equal to I, right? So B inverse A inverse as a matrix, it itself is a matrix, and it's multiplying. You're multiplying on the left of AB, and you're getting I. Now, also, we see that, well, if you start with AB and you multiply on the right by that same thing, and you multiply on the right by B inverse A inverse, well, then you see how the B and B inverse, B times B inverse is I, so you get AI A inverse. And then AI is A, so you have A inverse, and A times A inverse is I. And so this tells us that that AB times B inverse A inverse is equal to I. Okay, so given a matrix AB, if we multiply on the left by B inverse A inverse, we get I. And if we multiply on the right by B inverse A inverse, we also get I. Remember the definition of an inverse matrix, of an inverse, of a matrix being invertible. Okay, definition went like this. If for a given matrix A, if there exists a matrix capital B such that AB equals BA equals I, or let me write this, A times B equals I, and BA is equal to I, then the matrix capital A is invertible. And the matrix we found, matrix B, is an inverse of A. So for a given matrix A, if there exists a matrix B such that AB equals I and BA equals I, then the matrix A is invertible, and the matrix we found, matrix B, is an inverse of A. So what did we do? We found that B inverse A inverse, B inverse is a matrix, A inverse is a matrix, B inverse times A inverse is a matrix. This whole thing is one matrix. So this is a matrix where if we multiply on the left by AB, we get I, and if we multiply on the right by AB, if we multiply AB on the right by it, we get I. And so, as a conclusion, we conclude that this matrix B inverse A inverse, B inverse A inverse, is an inverse of the matrix AB, and also obviously that, get rid of obviously, and also that AB is invertible, right? Because we found the existence, we found some matrix, we found there exists a matrix where this happens. Okay, so this is from the fact that we found that AB times B inverse A inverse is I, and that matrix AB on the left, we multiply it by B inverse A inverse, and it equals I. And so that means the matrix AB has a B inverse A inverse has its inverse. Okay, and so another way to say B inverse A inverse is an inverse of AB is saying that AB inverse, the inverse of the matrix AB, is equal to B inverse A inverse. Okay, and so that we just proved the theorem. This is in words. This is written using notation. That was the theorem. So see that the inverse of a product of matrices is the product of their inverses in reverse order. So a good way to remember this theorem is that it says with conditions. So you need these conditions to be true. But it says with conditions that the inverse of a product of matrices is the product of their inverses in reverse order. It says with conditions that the inverse of a product of matrices is the product of their inverses in reverse order. Okay, and so AB inverse is B inverse times A inverse. Reverse order because instead of AB, it's B inverse A inverse. Okay. Example 9. The inverse of a product. So we're just going to find the inverse of a product of matrices. And so, so actually I'm going to do this on the whiteboard. So this is example 9. And it's the inverse of a product of matrices. So you're given that the matrix A is equal to the 2 by 2 matrix 1, 2, 1, 3. And you're given that the matrix B is equal to 3, 2, 2, 2. Okay, then that means, so then A times B, if you took A times B and you multiply them, then you would have this matrix 1, 2, 1, 3. And you would multiply it by the matrix 3, 2, 2, 2. And so this would be, well, this is a 2 by 2 matrix. This is a 2 by 2 matrix. The inner entries are the same, and the outer entries determine the size of the resulting matrix. And so the result of the product is another 2 by 2 matrix. So for the entry in the first row and first column, take the first row, first column, multiply corresponding components, add products. 1 times 3 plus 2 times 2. 3 plus 4 is 7. First row, second entry. First, select the first row here, the second column there. Multiply corresponding entries, add products. 1 times 2 plus 2 times 2. 2 plus 4 is 6. And just keep going. 3 plus 6 is 9. And 2 plus 6 is 8. So you get 7, 6, 9, 8. All right, and then since that's AB, you can find that the inverse of that matrix is equal to the inverse of the matrix AB. So the inverse of 7, 6, 9, 8. That's equal to, well, if the inverse exists, AD minus BC is non-zero. So AD minus BC here for the matrix AB is 7 times 8 minus 9 times 6. Right? 7 times 8 minus 6 times 9, right? You're just doing the determinant is just this times this minus that times that. And so that's 56 minus 54. So that's equals to 2. Okay, and so it's 1 over the determinant, which is 2, times switching the diagonal entry. So this is an 8 and that's a 7, and negating the off diagonal entries, -6, -9. And so you do 1/2 times each of those entries, you then get 4, -3, -9.5, and you get 7/2. So that's AB inverse. Okay, so that's AB inverse. And then if you find each inverse separately, A inverse is the inverse of A. So that's 1 over AD minus BC, 3 minus 2, which is 1, times, switch the diagonal entries of A, negate the off diagonal entries. And so that's A inverse. A inverse is this matrix, right? 3, -2, -1, 1. And then B inverse, well, the inverse exists if AD minus BC does not equal 0. That's 6 minus 4, which is 2. So determinant is 2, which is non-zero, so its inverse exists. It's invertible by theorem 1.4.5. The switch the diagonal entries, negate the off diagonal entries, and then so now it's 1/2 times that matrix. So you just take half of each entry, 1, -1, -1, 3/2. So that's B inverse. So we have A inverse and B inverse. We also have A times B inverse. Well, what is B inverse times A inverse? Well, B inverse times A inverse is the matrix B inverse that we found. Times the matrix A inverse that we found. 3, -2, -1, 1. And if you multiply those two, this is 2 by 2 times 2 by 2, which is another 2 by 2 matrix. The inner entries are the same and the outer entries are both 2. So this is 2 by 2. And you find these entries and you get 4 and you get -3. And then here you get -9/2. And then here you get 2 plus 3/2, so you get 7/2 here. Okay, so when you do B inverse times inverse, you get this. So this matrix is the same as this matrix. And so what we found is that A times the inverse of AB is equal to B inverse times A inverse. So we'll include for these matrices A and B, we found that in this one particular example, AB inverse is equal to B inverse A inverse. Okay, we know it's true in general if A and B are invertible, but we also found it specifically in this example to be true by direct calculations. Sorry, so A and B are invertible and the same size, right? So both A and B are invertible and the same size. That's just the other condition of the theorem. And so then the theorem says that AB inverse equals B inverse A inverse, and that applies here. That's what happens. Okay, so you can see that that's what happens. You can just use as a fact that if two matrices are both invertible and they're the same size, then the inverse of the product is equal to the product of their inverses in reverse order. Okay, if anyone has questions, you can just feel free to say out loud, ask a question, I'll answer. Okay, so some notes. B is a square matrix implies. So B is a square matrix, and that implies that, well, so the notation is that if you raise a matrix to 0 power, you get the identity. And if you take A to the nth power, oh, sorry, A is a square matrix. A is a square matrix implies that A to the square matrix to 0 power is I, and then A to the n is equal to A times itself n times. So there are n factors in that product. Factors is each of the things being multiplied. So A to the n means multiplying that square matrix by itself n times. And this is where This is where n is a non-negative integer. Okay. N being non-negative integer means that it's 0, 1, 2, 3, 4, 5, 6, and so forth. Or that n belongs to the set 0, 1, 2, 3, 4, 5. So those are the non-negative integers. Okay, so that's if A is a square matrix. Now also, A is invertible. That implies that A to the negative n is equal to the inverse of that matrix raised to the nth power. And so that means that if you have A inverse and you multiply it by itself n times, that's A negative 1, the nth power. This n vectors here in that product. And this is still where n is a non-negative integer, or that n is in the set 0, 1, 2, 3, 4, 5, 6, and so on. So n can be 0. Because then it's just A negative 1 to the 0 is just the identity. You need the fact that the matrix is invertible in order to think of its inverse. And once it's invertible, you can think of a matrix raised to negative powers. And that's just multiplying the inverse of the matrix n times. Okay, another note is that if you take a matrix A and raise it to the rth power, and you multiply it by a matrix raised to the s power, it's equal to that same matrix raised to the r plus s power. And if you take the matrix A and raise it to the rth power, and then you raise that to the s power, it's equal to raising that matrix A to the r times s power. These are just notes, okay? For facts. So theorem 1.4.7, if A is invertible and n is a non-negative integer, right? Or n is in the set 0, 1, 2, 3, 4, 5, and so forth, then part A inverse is invertible. And if you take A inverse and you want the inverse of A inverse, it's equal to A. The inverse of A inverse is A. B, this is if A is invertible. A to the n, where n is a non-negative integer, 0, 1, 2, 3, 4, 5, 6, and so forth. If A to the n is invertible, so then A to the n is invertible, and the inverse of A to the n is equal to A to the negative n, right? Which is A inverse to the nth power. So the inverse of A to the n is A inverse to the nth power. This is all assuming A is invertible and n is not, little n is a non-negative integer. C, Ka is invertible. It's another conclusion for any non-zero scalar K. And if you want the inverse of the matrix K times A, this is equal to the inverse of the number k. So it's not the inverse of a matrix, it's the inverse of a number, multiplicative inverse of a number times A inverse, the inverse of the matrix A. Okay, so example of C. An example of C would be the inverse of, let's say, 3A. Not being specific about it, just if you want the inverse of 3A, right, it would be the inverse of multiplicative inverse of 3 times the inverse of A. The multiplicative inverse of 3 is 1/3, and it's 1/3 times A inverse. Okay, so the inverse of the matrix 3A is 1/3 A inverse. 1/3 times A inverse. That's an example of what you do with the constant at the end. Okay, I'm going to write examples. I'm just going to add one more thing, which I think might be confusing. If you were to take, let's say, pi A, you want to know its inverse, the inverse of pi A, well, then that would be the multiplicative inverse of pi times A inverse. The multiplicative inverse of pi, you could just think of it as 1/pi, okay? And then that's times A inverse, right? So the inverse of the matrix pi A is 1/pi times A inverse. And you just 1 over any real number, basically. That's the idea. Okay, let's keep going. So example 11 is the square of a matrix sum. So let's say you take A plus B and you square it. Well, just like regular algebra, that would be A squared plus 2AB. Oh, sorry, let me do the math. A plus B, that's A plus B times A plus B. And so if you FOIL it out, you get A times A, which is A. You get plus BA, because it's B times A there. You get plus AB, because you have the A in the first parentheses times the B in the second one, plus B squared. See that?
Professor, can you scroll up for a second, please?
Is it about A plus B squared? I'm going to write it here.
Oh no, I was gonna look at the pi part, but it's okay. After you do the whiteboard.
No, okay. So here, the pi part. Yeah.
Yeah. Okay, let me just take a quick picture of it. No, I was copying down. That's why.
Oh, okay. You don't have a question. Okay.
Okay, I got it. Thank you.
You're welcome. Okay, so A plus B squared is A plus B times A plus B. And now you FOIL out. And so if you have A times A, that's A times A, which is A squared. And then plus, now if you have B times A here, that's BA. Then plus A times B. Then plus B times B. That's B squared. So that means you see how FOILing out, this is by FOILing. Process is called FOILing. I'm just going to call it that here. A plus B squared is equal to A squared plus BA plus AB plus B squared by FOIL. Okay, and so we get that. Now, if AB equals BA, then that implies that A plus B squared, which is still equal to this, is also equal to, well, the BA and BA are the same. So instead of, you could think of this as AB plus B squared. you could replace the BA here with an AB here. And that's because AB equals BA. Since AB equals BA, you could replace the BA here with the AB here. And now you can say it's equal to A squared plus 2AB plus B squared. Okay, but this is only if AB equals BA. It doesn't, when you multiply two matrices, you don't have to get the order of multiplication often matters, right? If it doesn't matter, if AB equals BA, then you can say that A plus B squared equals A squared plus 2B plus B squared. If they're not the same, then you have to think of it as the sum of four things, terms like that. And where these two stay separate, you can't combine them because they're different. Okay, and then so next is matrix polynomials. So if A is a square n by n matrix, and if P of x, which is equal to A naught plus A1x plus A2x squared plus dot 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 plus A n A m x the m, if that is any polynomial, then we define the n by n matrix P of A to be P of A is equal to A naught I plus A1 capital A plus A2 capital A squared plus dot 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 plus little a sub m capital A to the m. Okay, you're just replacing the unknown with the matrix capital A. And in the beginning, where you don't have the constant A, you have the constant A naught. You don't have the constant A naught, you have the constant A naught times the density matrix I. Okay, and so now you have this. So P of A is this is an n by n matrix because A naught I is an n by n matrix, A1A is an n by n matrix, A2A squared is an n by n matrix, plus dot dot dot, plus AM A to the m is an n by n matrix. And so you're adding n by n matrices, which means the sum is an n by n matrix, which means this definition, we're defining an n by n matrix and we're calling it P of capital A. Okay, so note here, P of A is obtained by replacing x with A and replacing the constant term A naught by A naught I. Okay, the expression for P of A which is this expression, or that expression, just gonna write expression for P of A. For the expression for P of A, that expression is called is called a matrix polynomial in capital A. So this is called, that is called a matrix polynomial in A. Right. All right. Any questions about anything? Okay. So let's look at example 12. Let me just look at something real quick. Okay, so next is example 12. And it's a matrix polynomial. Okay, so the example is find P of A for P of X is equal to X squared minus 2X minus 3. And A is equal to the 2 by 2 matrix. -1, 2, 0. Right, so we just substitute the matrix A into that polynomial, and the constant is now replaced with the constant times the identity matrix. That means that P of A is equal to A squared minus 2A minus 3I. That means that's equal to the matrix -1, 2, 0, 3 squared minus 2 times that same matrix, -1, 2, 0, 3 minus 3 times the identity matrix, 1, 0, 0, 1. Right, and then that's equal to, so if you square that matrix, you multiply it by itself. If you multiply it by itself, you get a 1 here. You get a you get a 4 here. You get a 0 here, and you get a 9 here. Okay, so it's multiplying this matrix by squaring that matrix. That's minus, and then this is, I'm just multiplying this by 2 and keeping the minus sign. So this is -2, 4, 0, 6, and then minus 3 times that matrix. So I'm keeping the minus sign. So I'm only multiplying by 3, not minus 3. And so it's minus this by 3. That's 3, 0, 0, 3. Okay, and so then you do all this arithmetic here. And so you just add, so now you just 1 minus -2 is 3. 3 minus 3 is 0. So this entry is a 0. 4 minus 4 is 0. Minus 0 is 0. 0 minus 0 is 0. 0 minus 0 is 0. 9 minus 6 is 3. 3 minus 3 is 0. Let's see, get that. And so P of A is equal to 0. So P of A is equal to 0, where 0 is the 2 by 2 0 matrix. All right, and so that's that example. Okay, the next thing are properties of the transpose. Theorem 1.4.8. If the sizes of the matrices are such that the stated operations can be performed, then the following are true. If you take the transpose of a matrix and you take its transpose, you get back the original matrix. B. If you take A plus B and you take its transpose, it's equal to A transpose plus B transpose. C. If you take A minus B transpose, it's equal to A transpose minus B transpose. D. If you take the matrix K times A and you take its transpose, it's equal to K times the transpose of A. E. If you take AB transpose, it's equal to B transpose A transpose. So just like when you take the inverse of a product of matrices, it's the inverse of the product. It's a product of their inverses in reverse order. If you take the transpose of the product of matrices, it's equal to the product of their transposes in reverse order. Okay. In words, this says that the transpose of a product of matrices is the product of their transposes in reverse order. Right. So that's E. Right. So that's theorem 1.4.8. Theorem, and keep in mind that the transpose is unaffected. This K just moves out, and you don't. You can just still multiply by K. Okay, because taking the transpose involves switching orders and columns. You don't actually change the entries themselves. You just kind of reorient them. So you don't need to change the constant K. It stays K times. The K stays as it is. You're not flipping it or anything. Okay, so theorem 1.4.9. If A is an invertible matrix, then a transpose is also invertible. And try asking yourself, what is the inverse of A transpose? The inverse of A transpose is A inverse transpose. So the inverse of A transpose is the transpose of A inverse. The proof of that well, if you take the matrix A transpose and you multiply it by A inverse transpose, then that's equal to, so here, right, if we take the transpose of a product, it's equal to the product of the transposes in reverse order. This is a product of transposes. And if we think of this as the reverse order of something, and that means that the original order would have been A inverse A. And then we're taking the transpose of it. So the transpose of A inverse times A is equal to A transpose times A inverse transpose, right? It's the reverse order. And so A inverse A, though, is I. And so in the parentheses is A inverse A, which is I, and we take the transpose of it. If you reverse the rows and columns of an identity matrix, you still have the identity matrix. Okay, let me show you that. So what I'm saying is that I transpose equals I. So if you have an identity matrix, say you have an identity matrix, and they come in different sizes. Let's say we start with a 2 by 2 identity. We think of a 2 by 2 identity matrix. Then if we take the transpose of it, we're just flipping the rows and columns. And so if you think of the first row, that becomes the first column. And so if the first row becomes the first column, then you have a 1, 0 here, right? Black. And you have a 1, 0 here. And the second row is this. And then you make it the second column. Now it's 0, 1. And so now you get 0, 1. The end result is just, I'm not doing anything, I'm just rewriting it without the colors here. You have 1, 0, 0, 1. That's still I. I transpose for a 2 by 2 identity matrix is I. And then you could do it for any size matrix. So in general, the transpose of an identity matrix is the identity matrix itself. Okay. So here, when we take I transpose, it's still I, so equals I. So we show us that A transpose times A inverse transpose is equal to I. Also, if you take A transpose and you multiply in the left by A inverse transpose. So if you take A transpose, originally we had A transpose and we multiplied it on the right by A inverse transpose and we got I. Now if we take A transpose again and we multiply on the left by A inverse transpose, then what we get is, well, this is a product of transposes, right? When we have a product of transposes, we can think of it as the transpose of a product of matrices before we reverse the order. So if before we reverse the order, you can think of that as A times A inverse. And then we're still taking the transpose of it. So right, so if we have a product of transposes, we can think of it as the transpose of a product of those matrices before you reverse order. And so now it's A inverse transpose. A inverse is still I, so this is I transpose, and I transpose is I. So what we now know is that if you take the matrix A transpose, right? If you take the matrix A transpose and you multiply on the right by A inverse transpose, you get I. And if you take the matrix A transpose and you multiply on the left by A inverse transpose, you also get I. And so we see that, so what we see is that A transpose, A inverse transpose equals I, and A inverse transpose times A transpose is equal to I. By the definition of an invertible matrix, we now have that that A transpose is invertible, and that the inverse of A transpose, is equal to that matrix we can multiply it on the right and left by and get I. So specifically, this matrix is its inverse. A inverse transpose. So A inverse transpose, this thing, has to be the inverse, an inverse of A transpose. So inverse of A transpose equals A inverse transpose. And so that's what we just proved. And so we're done. Okay. So then there's that proof. If anyone has questions, just interrupt me anytime. Okay. Because that's theorem 1.4.9 and its proof. So let's look at another example, this time on the whiteboard. So this is example 13, and it's the inverse of a transpose. So we're going to think of a general 2x2 matrix and its transpose. So if you have a general 2x2 matrix called capital A with entries A, B, C, D, that's a general 2x2 matrix. And if you think of its transpose, A transpose then is switching the rows and columns. So if you switch the rows and columns of this matrix, the first row becomes the first column. And the second row becomes the second column. So you get, these are the entries of A transpose, right? In that order. We could have done columns also. We could have said the first column with AC is now the first row of A transpose AC, and the second column, ABD, is the second row of A transpose BD there. So you could have done it that way. Okay, so we're assuming, so by our assumption, we're saying that this is invertible. Okay, so assume A is invertible. So assume A is invertible. And so since A is invertible, that implies that A times D minus B times C does not equal 0. Right? A times D minus B times C. A times D minus B times C does not equal 0. Right? The arrow going to the right means positive, arrow going to the left means negative. So A times D is positive, minus B times C. The minus sign goes to the left. Okay. So that's non-zero because A is invertible, and that's by theorem 1.4.5. So this is by theorem 1, theorem 1.4.5. Okay, so but now notice that the determinant, I think, what is the determinant of A transpose? The determinant of A transpose is equal to, you just look at it right here. It's AD minus CB. AD minus CB is the same thing as AD minus BC for real numbers. And so that means that this is also not 0. Okay, so we're not given this is non-zero, but because A is invertible, we know that AD minus BC is non-zero by theorem 1.4.5. And that means the term A transpose is non-zero. And that implies that A transpose is invertible. So that implies that A transpose is invertible and that the inverse of A transpose by theorem 1.4.5 is saying it's 1 over the determinant of A transpose, which is AD minus CB, times, now you switch the entries on the main diagonal, so this becomes DA, and negate the off diagonal entries. So this is negative C, negative B. And so now the inverse of A transpose is that. And so you would just multiply each entry by 1 over AD minus BC. So you get D over AD minus BC, negative C over AD minus BC, negative B over AD minus BC, and A over AD minus BC. Yep. Okay, and so that's A transpose inverse. And then if you do the same thing with A inverse transpose, you can see it's the same. So if we found A inverse on the side here, we could just, if we found A inverse would be 1 over AD minus BC times ABCD. And then if we took A inverse and we took its transpose, and I'm going to just do this quick, I'm skipping a little bit here, then you're just switching the rows and columns, and so you get oh, sorry, you gotta change the entries here. Okay, so you switch the diagonal entries, negate the off diagonal entries, and that goes there. Okay, now that's A inverse, and then you take the transpose of that, and so you get D over AD minus BC. You get negative B over AD minus BC. You get negative C over. That's because you're switching the rows and columns because you're taking the transpose. And then you get A over AD minus BC. So you see is that this matrix, A inverse transpose, which is the same as A transpose inverse. They're equal. And so the conclusion, we have that A transpose inverse is equal to A inverse transpose. Is exactly what the theorem says, but we saw it was true through calculations for a particular example. If A is invertible, then this is true in general. Okay. And let's keep going. 1.5 is on elementary matrices and a method for finding A inverse. Okay, so the goal is to develop an algorithm for finding the inverse of matrix, and to discuss some of the basic properties of invertible matrices. All right, so first, in order to develop a method for finding A inverse, to develop this algorithm, we have to first talk about what's called elementary row operations on a matrix A. Okay. So there's things called elementary row operations on a matrix A. And so there's three of them. These are the three. The first one is multiply a row by a non-zero constant C. That's an elementary row operation on a matrix. multiplying any of its rows, single rows, by a non-zero constant C. The second elementary row operation is interchanging two rows of matrix A. Okay, that's also an elementary row operation. And the third one is add, this is the hardest one, add a constant C times one row to another. Okay, so keep in mind that the row that you're changing is the another one here. So I'm going to highlight the word another because I want to emphasize the fact that what's changing in the matrix is the quote unquote the another matrix. You're taking a constant C times one row and you're adding it to another one. And so the one that's being added, the one that you're adding it to, that row is changing. The original row that you multiplied by constant C is not changing by this operation. You're only multiplying it by a constant so that you can take that multiple and add it to the other row. And so it's the other row that's actually changing, not the row that you're in your head multiplying by a constant. Okay, so if we let capital B be the matrix that results from A by performing one of these elementary row operations, in the list, then the matrix capital A can be recovered from B by performing the corresponding operation in the following list. Okay, so what did I just say? So if well, let me just say it again. If we let capital B be the matrix that results from A by performing one of these elementary row operations, then the matrix A can be recovered from B by performing the corresponding operation in the following list. So let me write the first one on the list first. The first one on the list, this corresponding list, is multiply the same row by 1 over C. That's of course, this is a corresponding operation to the first operation, which is multiply a row by non-zero constant C. Okay, I'm going to come back to this list, so don't worry. I'm just going to explain something, the idea of this, this first one, so that the other ones make sense. If you start with a matrix, let's say you start with the matrix 1, 1, 4, 7, and let's say you multiply row 1 by 10, by the number 10. Okay, I'm gonna have to. You multiply it by the number 10. Okay, so you multiply row 1 by the number 10. Well, what would that result in? That would result in a matrix where the first row, all the entries are multiplied by 10. So it would be 10, 10, 4, 7. Now that's the first elementary row operation in the list. So looking at this list, the first elementary row operation is multiply a row by a non-zero constant C. Our non-zero constant C here is 10. Okay, that's an elementary row operation. Now, what we want is we want to recover the original matrix from this new matrix. So we have a new matrix from the old one because we multiplied the first row by 10. Correspondingly, there's a corresponding operation to the original elementary row operation of multiplying the first row by 10. That corresponding operation is multiply the first row, multiply row 1. by 1/10. Okay, so now you can take the first row of the new matrix and multiply it by 1/10, and then you'll get the original matrix back again. So our elementary row operation was multiply row 1 by 10. The corresponding elementary operation was multiply row 1 by 1/10. And so we can reverse the effect of these elementary row operations by performing its corresponding elementary row operation. Okay, so for any elementary row operation, there is a corresponding one which will negate the effect of it. So if we do one, then the other, we get back to where we started. In a sense, it's the inverse of that elementary row operation. Okay, so the corresponding inverse operation of multiply a row by non-zero constant c is multiply the same row by 1/c. So multiply a row by non-zero constant 10, its corresponding inverse operation is multiply the same row by 1/10. Okay, it was the first row that we multiplied by 10, right? And so the inverse operation had to be multiply the same row, row 1 by 1/10. If we had multiplied the second row by 10, then the inverse operation would be multiply row 2 by 1/10. Make sense? So the row matters, right? This elementary row operation is specifying a particular single row of your matrix and multiplying it by a constant. You need to multiply that same row by the reciprocal 1 over that constant to get back to where you started. Okay, so that's the first inverse operation. So this is the inverse operation of the first elementary row operation. It is not an inverse operation for 2 or 3, okay? If you do operation 2 or 3, you need a different corresponding inverse operation to get back to where you started. So this is only for the first elementary row operation to get back. The second corresponding elementary row operation, this is the corresponding one to the second one, making it simple, is just interchange the same 2 rows, okay? So if your elementary row operation on matrix is interchanging 2 rows, then the corresponding inverse operation to get back to where you started would be to interchange the same 2 rows. You can't interchange 2 different rows because then you could get something different. If you interchange the same 2, though, you'll get back to where you started. So for instance, if you have a 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 0, 0, 0. And let's say we perform the elementary row operation, interchange rows 1 and 2. So if we interchange rows 1 and 2, the resulting matrix that we get is 4, 5, 6, 1, 2, 3. And we're only interchanging the first 2 with each other. So the third row stays unchanged and still 0, 0, 0. So that's if you interchange rows 1 and 2. So the inverse of that operation, the operation you have to perform after it to get back to where you started, is to interchange the same 2 rows. So you have to interchange row 1 and 2 again. So if you interchange the same 2 rows, interchange rows 1 and 2, again, you get back to where you start, right? If you switch 2 things and you switch them again, you're right back where you start. So then you interchange rows 1 and 2 again, and you get back to where you started. Now interchange those 2, and then you're back 1, 2, 3, 4, 5, 6. Right? So this is another corresponding elementary operation. This is the corresponding one to the second elementary operation. Now, so there's the third one. This is the hardest one. The original elementary operation was add a constant c times 1 row to another one. This is now the inverse elementary row operation to that elementary row operation. And it says if capital B resulted by adding c times row r sub I of A to row r sub j of B, I mean, it's r sub j of still A of A. Okay. Then add negative C times row R sub j times R sub I. Then add negative C times row R sub I to row R sub j. Okay, the notation, it's easier if you just know what it does than to it's easier to first see what's happening rather than see what the notation's saying. Once you get it, once you know it and you understand notation, you can write this out and it's not too complicated. But it's the idea that you need to know in order to be able to write all this silliness. So let me give you an example. Okay. First, we're going to add a constant C times one row to another one. So let's start with the matrix 1, 2, 8, 16. Okay, I'm going to add 2 times row 1 to row 2. So we're going to add 2 times row 1 to row 2. So I'm going to circle row 1, and by circling row 1, I don't mean I'm changing row 1. I'm adding 2 times row 1 to row 2. So row 1 is going to stay exactly the same. It's still going to be 1, 2. I'm going to take 2 times that row. I'm going to add to row 2. And so I add corresponding entries. So 2 times the 1 is 2, and I add to 8 and I get 10. So first see how I get that 10. I'm taking 2 times that 1 and I'm adding it to the 8. So it's 2 plus 8, which is 10. Now I'm taking 2 times the 2 in that row also. So that's 4. And 4 plus 16 is 20. Okay, so adding 2 times row 1 to row 2 changes row 2. It does not change row 1. So the way to remember it is to think of the thing you're multiplying by a constant, that row stays the same. And then the other row is what's changing. So I'm adding 2 times row 1 to row 2. Row 1 stays the same, and row 2 is now been added. You now added 2 times row 1 to it, and you've got this one. Okay, that's our original elementary row operation. That's the third one for specific rows and specific constant for specific starting matrix, right? So right, we can have the same instruction to add 2 times row 1 to row 2. If we start with a complete different matrix, then we have different operations, right? But okay, so this is an elementary row. This is the third. This is an example of the third one on that list. So now we want an inverse operation to get back to where we started. Okay, so how do we get back to where we started? Well, what did we do? We took 2 times the first row and we added to the second. Well, if we added 2 times to the second, then to reverse it, we have to add negative 2 times to the second, right? It's like if I gave you 2 things, to reverse it, I would have to take away 2 things, right? If I gave you 2 apples, to reverse it, if you had a certain amount of apples and I gave you 2 of them, to reverse it, I'd have to take away 2 of them, right? If you started with 20 apples and I gave you 2, you'd have 22. And to reverse it, I'd have to take 2 away and you'd have 20 again. If you have row 2 of your matrix and I give you 2 times row 1, then to negate the effect of giving you 2 times row 1, I have to take away 2 times row 1. That's now I need to add negative 2 times row 1. To row 2. Okay, and so then if you take looking on the right, I'm looking on the right now. I don't know if you can see the cursor on the screen as I'm moving it. If you add -2 times row 1 to row 2, then look at the first entry. You're taking -2 times the 1, which is -2, and you're adding it to 10, and you get the 8. Then if you take -2 times the 2, you get -4. -4 plus 6 plus 20 is 16. So adding -2 times row 1 to row 2 gets you back to where you started. Okay, so again, if you add 2 times row 1 to row 2, to negate the effect, instead of adding 2 row 1s to row 2, you have to now take away 2 row 1s from row 2 to negate the effect of adding 2. You subtract 2 row 1s. All right, and so now that's the inverse operation for a specific, in a specific case, right? So the general expression is just a way of using, it's a way of explaining a very general situation, okay? Because here we had specific rows. We're adding a specifically 2 times, specifically row 1 to specifically row 2, right? We could have chosen different rows, or we could have chosen different concepts. And we could have chosen a different starting matrix. So we just need to express this idea in general terms. That's why it looks confusing. But the idea is very simple. You're just taking a multiple of one row and you're adding it to another. And to negate the effect, you're adding the negative of that amount of that same row to the other row. Okay. So adding 2 times row 1 to row 2, the opposite is adding -2 times the same row 1 to row 2. If we had a 4x7 matrix and we took 2 times row 3 and we added it to row 2, the opposite would be adding -2 times row 3 to row 2, right? You would keep the rows the same. You keep the rows and where they are, right? Like the effect, right? The row you're multiplying by constant, you would keep that the same, and the row you're adding it to would be the same. Okay. So here back on Word, I explained that operation in general terms in this way. If capital B resulted by adding C times row Ri of A to row J of A, then add -C times row I to row Rj, right? Does that make sense? So you're taking C times row Ri and adding it to row J. So the opposite is adding -C times row Ri to row J. Right? It's just saying instead of 2 times row 1 to adding 2 times row 1 to row 2, and then adding -2 times row 1 to row 2, instead of adding C times row Ri to row Rj, and then the opposite is adding -C times row Ri to row Rj. All right, and so that's the inverse operation of the original operation, add a constant C times one row to another. Okay, so now we have 3 elementary row operations on a matrix, and we have correspondingly 3 corresponding elementary row operations. These are each examples of the original 3. So when I say there are 3 elementary row operations, and there's 3 corresponding ones, I'm not saying that there are 6 elementary row operations. There are still only 3, right? The inverse one is just another example of the first one, but it's just a very special one. It's a special case of the first one, which negates the effect. So multiplying the same row by 1 over C is still an example of multiplying a row by constant, okay, by non-zero constant. Once you multiply a row by non-zero constant C, multiplying a row by 1 over C is still multiplying by non-zero constant. 1 over C is also non-zero. And so this is not another type of elementary row operation. Same thing with 2, right? You're interchanging 2 rows. The corresponding one is interchanging the same 2. It's still the same element, same type of elementary row operation. And the third one, adding a constant C times 1 row to another. The corresponding one is still adding a constant of 1 row to another row. Okay, so we have only 3 elementary row operations, but for any elementary row operation to perform on a matrix, there is a specific corresponding one, which is of the same type, which negates its effect. Okay. All right. And so what we can say as a conclusion to all of that, and then this class ends. B, if you starting with B is obtained from A by performing a sequence of elementary row operations, that implies that Well, if B is obtained from A by performing a sequence of elementary row operations, that implies that there is a second sequence of elementary row operations, which when applied to B recovers A. Okay, so I'm just going to illustrate this idea. So you're obtaining, if you start with B is obtained from A by performing a sequence of elementary row operations. So then in the beginning, you start with A and you perform a sequence of elementary row operations on it. And then eventually you get to B, right? And where the arrows are elementary row operations. Then there is a corresponding sequence of elementary row operations where each one is the inverse of the other operations. And so if you perform that sequence, you get back to A. Make sense? So if you start at A and by a sequence of elementary operations get to B, then in the reverse order, if you take the corresponding elementary operations in reverse order, then you can go from B to A. Okay, so if you have your first elementary operation, then your second one, then your third one, then your fourth one, then your fifth one, then dot, 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 then your nth one, then the inverse elementary operation of the nth one, I'm going to call it, so then, right, so then you have the inverse of the nth one, dot, 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 the inverse of the fifth, then inverse of the fourth, then inverse of the third, then inverse of the second, and then inverse of the first, and you get back to restart. And so that's the concluding statement I have here about that. Okay, and so we finished 1.4 near the end of class. And so now that means I can assign the homework. So for next class, I'm assigning homework. And so the homework is, we go to, so the homework is for 1.4. So I'm assigning this exercise set 1.4. Okay, so this is due next class, the exercise set for 1.4. Numbers 1, 9, 13, 18, and 32. One, 9, 13, 18, 32. 1, 9, 13, 18, 32. This is exercise set. Okay, so exercise set 1.4, 1, 9, 13, 18, 32. 1, 9, 1, 9, 13, 32. Exercise set 1.4. Okay, and so this is for next class. All right, and so that's it. And so I'll see you next week on Tuesday. Okay, have a good night. You too, okay. Oh, I'm going to save the whiteboard.
Bye, Professor. Have a good night.
Good night. Don't forget to remind me about the whiteboard. Okay.
Good night, Professor.
Good night.